Copyright in these lectures is either owned by the ANU or a third party who has licensed the ANU to use it. Students may use the recording for personal study only. No lecture may be communicated online, copied or shared without the prior permission of the ANU.
Okay, let's start today's lecture, and I think it's the second last lecture of this course, and really thanks for your coming. And firstly, still some announcement. So the first announcement is about final consultation hours, so you can see the final consultation hours of myself and also the 5 tutors. So basically, I think you have 5 hours, not 5, 7 hours consultation, final consultation hours. So you can, if you have any questions, you can consider to attend any of the consultation hours. And sorry that I need to notice I'm going to travel to visit my collaborator during November 1st to 12th. So during this period of time, if you have any questions and if you need some consultation, you can try to join the consultation hours of tutors. So that's about final consultation hours. And obviously, the final exam is on November 14th. So I think you should receive the emails. And that's about final consultation hours. And another announcement is about exam sample questions. So I will upload exam sample questions later today, so you can have a look at it. I think the exam sample questions and also solutions, I will upload both. And the last one is about the assignment 2. And I think the tutors and I have almost finished marking. So I think for the students who will have tutorials, I think later this week, maybe tomorrow, so you can get your assignment back during your tutorials. So for those students who have already had their tutorials, I think you can get your assignments, I think, from the administrative office, I think maybe next week, and I will announce that on Wattle, so you need to be very careful about that and notice that information and get your assignments after today's tutorials or next week from the administrative office. So I think that's basically all the announcement I want to say. So any questions? Any questions about final exam, assignment, and also questions about previous lecture content? Okay. Okay, let's just try to, sorry. So let's try to continue the previous topic. So what I need to tell you here is that this topic, Bootstrap, I think I have already emphasized. This topic, Bootstrap, is maybe the most difficult topic, I think, in the second half of the semester. And also this topic is included in your final exam. But do not need to worry too much about this topic. So as long as you can understand the lecture notes, I think there is not a problem for it. And in the previous lecture, so basically we review the simulation. So what's the advantage of simulation? So basically the simulation in this course mostly can help us approximate the sampling distribution of estimation. And because it can be used to approximate sampling distribution, so obviously it can be used to approximate mean and also standard deviation of the estimation. So I think these two are the most important use of simulation in this course. And the reason why I introduced simulation earlier is just to help you understand Bootstrap, because you will find that Bootstrap basically inherits a lot of properties from simulation. But the difference between the simulation and the Bootstrap here is that for Bootstrap, Bootstrap is usually used to solve the real data problem. So that means we only have one data set. So that's usually what we face in our real application. So that means we only have one data set with observations. Here we have 10 observations of Z, so that our observations is Z1, Z2 until Z10, and also X1, X2 until X10. So we only have 10 numbers of Z and 10 numbers of X. So that's our real data set. So that means we only have one data set. So in order to use the simulation idea, we actually need to generate 1,000 data sets. But how to make one data set into 1,000 data sets? So basically, that's the first problem we need to solve. So in order to solve this problem, we propose this drawing balls with replacement. So it's actually from your introductory level of statistics course. So we just randomly draw balls from a bag. Here we have 10 balls. And because it's drawing with replacement, so that means we can have repeated numbers for those balls. And we draw the balls, I think drawing balls, this kind of experiment. We implement this experiment for 10 times, and then we obtain 10 numbers of balls here, and then we put it on the right. So that's our result of the experiment. So how can we do that? By using R. So in order to realize drawing balls with replacement in R, we use this sample function. So this sample function just means that we randomly draw balls with replacement from 1 to m balls. So that means the number of the balls are from 1 to m. And we want to conduct this experiment for 10 times. So here size equals to m means we conduct this experiment for 10 times, and then we obtain 10 numbers of balls. And the replace equals to true just means that we consider draw balls with replacement. So by using this sample function, we can actually realize drawing balls with replacement in R. And the output here is 2944772367. So that is the experiment result. And also we can try second time. So when we try second time, we can have different numbers. So this is the result for those numbers of balls after we conduct the experiment. So we can keep on doing the above procedure until 1,000 times. So how to use this drawing balls with replacement idea to generate 1,000 data sets? So in order to generate 1,000 data sets, recall that we have our original data. So these are our original data from Z1 to Z10 and X1 to X10. And in this case, we can just treat each observation as one ball. For instance, we can just treat Z1, X1 as ball number 1, Z2, X2 as ball number 2, and Z3, X3 ball number 3, and so on and so forth until ball number 10. So the next step is just to draw balls with replacement from 1 to 10. And how to do that? By using this sample function, right? And the drawing result here is 2944772367. So that means we save the drawing results in this boot IND object. So that means our output here, boot IND, is a vector of this. So that means boot IND saves the output of drawing balls with replacement for 10 times. And then, based on this number of balls, we can correspondingly obtain the new data set. So for instance, if we draw the number 2 ball in this experiment, so here we draw number 2, then the corresponding data here is Z2X2. So that means we actually put the number of the balls here, the number of the ball here as the index of Z and X. And similarly, if we have our output to be number 9 ball, then correspondingly we have our data Z9, X9, and also we have Z4, X4, and Z4, X4, and Z7, X7, and the last one is also Z7, X7. So that's how we obtain our new data. But how to realize this idea in R? So remember that the boot IND is actually a vector of 2944772367. And remember that in R, we can use the square bracket to get some values from a vector or from a matrix. So here, what we want to get is just to obtain the second, the ninth, the fourth, the seventh, the second, the third, the sixth, the seventh elements from the Z vector. So what we can do here is just to put those number of the balls in boot IND and then put those boot IND inside the square bracket. And in that case, you can obtain the corresponding value of Z. So here, we should have the Z2, Z9, Z4, and so on and so forth until Z7. So that is the data, the new data of Z by using this drawing balls with replacement idea. And similarly, if we put the boot IND, which is actually a vector of the number of the balls we draw, in this case, we can obtain the new data X. So that's how we realize this drawing balls with replacement, and then we use this idea to generate the new data set of Z and X. So in this case, we have a new data set Z here. So this is the new, our new data set Z, and this is the new data set of X. And in order to help us to write down this kind of idea easily, so we actually try to use some notations to help us to understand. So here, our output here is Z2, X2, Z9, X9 until Z7, X7, but we can write those new data set by using this star notation. So the star notation just means bootstrap sample. So if you see the star notation here, so basically that just means the bootstrap data set, or you can call it bootstrap sample. And we can write it as Z1 star until Z10 star because we still have 10 observations. Because we draw balls with replacement for 10 times, so we still have 10 observations. So for the bootstrap data, we still have m equals to 10 observations. So we use Z1 star and Z10 star to represent this output of the new data of Z. And also similarly, we can use X1 star until X10 star to represent the new data of X. And also we use this parenthesis 1. This parenthesis 1, here we all have 1, means it's the first bootstrap data set. So that means we can have second and also third, fourth, and so on and so forth. So that's how we obtain the first bootstrap sample. I think you may still need some time to process it, but let's look at the second one. So in that case, you may feel a little bit familiar, and I will repeat it again. So in order to get the second bootstrap sample, basically we just repeat the above procedure. So in the above procedure, what we have done is just to consider our data from 1, 2, 3, 4 until 10 as 10 balls with numbers 1, 2, 3, 4 until so on and so forth until 10. And then we use this sample function to draw balls with replacement for 10 times, and the output are the 10 numbers of balls. So the numbers are 6, 6, 6, 6, and so on and so forth. The last one is 3. So that's the number of balls we have drawn from from this experiment. And this boot IND is actually, the meaning is bootstrap index. The boot IND here is a vector which saves the vector values of this. So that's the result of the drawing balls with replacement. And then we just put those numbers as the indices of our new data. So that means we actually obtain our new data as, for Z, we have Z6, 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 and so on and so forth. The last one is Z3. And similarly, we have our new data of X, X6, 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 until X3. So that's the second bootstrap sample, or we can call the second bootstrap data set. And in order to easily represent this new data, we use this star notation. So we have here, firstly, it's the bootstrap sample, so we use star. So we have Z star. And also, it's the second bootstrap sample. So basically, it's the second data set. So we use parenthesis 2. And here, it's the first observation of the new data, so we use Z1. So here we use Z1 star parenthesis 2 to represent this 13. And also we can have Z2 star parenthesis 2, and so on and so forth until Z10 star parenthesis 10, not 10, 2, sorry. Because we still have this second bootstrap data set. And similarly, we can just write those down as x1 star 2 until x10 star 2. So that's how we obtain the second bootstrap data set. So basically, we can keep on doing the above procedure, and then we can obtain R repeated bootstrap samples. So here, we usually consider R equals to 1,000. So here we have 1,000 data set. So for each data set, we have I from 1 to m observations. So for each data set, we have i's from 1 to until m. Here m equals to 10 observations. And also we use star to represent that we have the bootstrap data set. And here we have the data set from number 1 to number r equals to 1,000. So that means we have 1,000 data sets. So that's the reason why we try to use some notation to help us to know that we are actually dealing with the bootstrap data sets by using this star and also the parenthesis notation. So how to do that? How to realize that? How to obtain 1,000 data set in R? So if you still remember the simulation, you will find that the only difference here is this part. So this is the only difference. So in this part, basically, we try to use the drawing balls with replacement to help us to obtain the data. To obtain the data. And then what we can do here is just to save the data in this matrix Z star data and X star data. So what's Z star data? So here, before we implement this loop, we actually need to keep some space to save the bootstrap data set. So Z star data is actually a matrix, and here you can see the row number equal to R, so that means each row represents one data set of Z. So here, each row consists of one data set of Z. And also the column number here equals to m, so that just means that for each row we have 10 observations. So if you have a look, you can compare the codes for simulation and codes for Bootstrap. This part and this part, and also including the for loop, are exactly the same. So the only difference here is just that we use different methods to generate the data set. So maybe you can have a look, and then we can compare this part of two codes. So this is the simulation, if you still remember. So in the beginning, before the loop, we also need to keep some space to save the X data set and also Z data set. And inside of the for loop, we need to consider to use the model assumptions, the Poisson model assumptions, to generate our data of Z and data of X. And then we just save the data of Z and data of X in this data matrix, Z data and X data. So this is for the simulation. So the only difference is the part here by using the assumptions. by using the model assumptions. So this generation of data are from model assumptions, and also in this case you need to know the true values of beta 0 and beta 1. Otherwise you cannot generate the data, so this is for simulation. But for Bootstrap, the only difference here is that we consider to use this drawing balls with replacement to generate the data. And in this case, we only need one data set. If you still remember, Z1 to Zm and X1 to Xn, m equals to 10. And we do not need to know the true values of beta 0 and beta 1. So that's the difference between the Bootstrap. And this is exactly the case for James. So if you still remember James, so that means when we deal with the real data, so when we deal with the real data, we have one data set, but we have no idea about the values of beta 0 and beta 1. But we can still generate 1,000 data sets. And also, if you look at the first row of Z data star data and X star data, and also you can have a look at the second row for this data set matrix. So you will find that the first Bootstrap sample of Z here, 10, 26, 7, 7, 12, 12, 10, 10, 13, 12 here, is exactly the same as what we have generated here. So basically, because we just repeat the procedure, the first Bootstrap, the second Bootstrap, and so on and so forth, so we should have the exact same result here. So this is the first and the second Bootstrap sample. So this is the first Bootstrap data set, and this is the second Bootstrap data set. So in this case, we try to use this simple idea, drawing balls with replacement, to generate 1,000 data sets. But different from simulation, we have different generation procedure. So this is the different generation procedure. And this kind of procedure is exactly called Bootstrap. And the data sets are called Bootstrap samples. So in conclusion, we only use one data set to generate 1,000 data sets without knowing the true values. And in this case, for James, he has 1,000 Bootstrap data set for James. And these data sets obviously are different from the 1,000 data sets that Li-Lei has. So Li-Lei has the 1,000 data sets from simulation. So 1,000 data sets from simulation. And obviously, these two data sets are not the same. So the question here is that for James also now, he also has 1,000 data set. So the question here is that can he use these 1,000 data sets to realize something similar compared to delay? So that's the question. So that means what Lillet can do by using his 1,000 data sets can be, whether or not can be used in this 1,000 bootstrap data sets. And I give you the answer directly. The answer is yes, and we will look at the details and how to do that. But before that, we need to mention one professor, which is very famous in Australia, and he's an Australian. And I think surprisingly, you will find that he was actually the top 1 statistician in the world, even though so you can see the statistics in Australia is actually very strong in the world, or used to be very strong in the world. And unfortunately, he passed away 2 years ago, and he was a professor in Australian National University from 1978 until 2005, and his name is Professor Peter Hall. And he has this very famous book, Bootstrap and Address Expansion. And so basically, if you read this book, you will find that he actually gives a lot of explanations and theoretical results to confirm that actually James can use this 1,000 bootstrap data sets to realize something similar compared to what Lillet has done by using his 1,000 simulation data sets. So from the theoretical point of view, we actually have very good properties for this bootstrap based on this book and based on the contribution of this professor. And this professor is really famous, and also I mentioned that he was the top 1 statistician in the world, and also he had a lot of very famous students, and we have some in my school. So for instance, Professor Michael Martin, who teaches graphical data analysis, was his student, and Professor Alan Welsh, who teaches advanced mathematical statistics, was also his student, and also my supervisor was his student. So yeah, his really his contribution to the bootstrap, I think, is really huge. And also in his book, he used this nested Russian dolls to represent the idea of bootstrap. So here we have this kind of nested dolls, right? And by using this, he actually explains what's the meaning for bootstrap. So usually for doll 0, so which is the biggest doll, usually we can consider it as our model. And for model, we usually need to know the parameters beta 0 and beta 1. And by using model, we can actually perform simulation. So by using the simulation, we can generate our data and also sample, or you can call it sample. And in our case, we can generate Zi, Xi, and I is from 1 to n. And you can consider the data generated based on the model here can be treated as doll number 1. And also by using one data set, we can actually generate 1,000 bootstrap data set. So that means we can use the drawing boards with replacement idea to generate the bootstrap sample. Which is Zi star, Xi star. I is also from 1 to n. And we can just treat it as the doll number 2. So we can actually keep on doing that. We can have door number 3 and also door number 4. So door number 3 here, you can, so there is actually a name, which is called double bootstrap. And the door number 4 is the triple bootstrap. I think you can, if you are interested, you can keep on doing that. So that's some comment from Professor Peter Hall, and I think it's really active by using, I think, something in our real life to explain what is Bootstrap. So I think basically I have explained how to generate the data, Bootstrap samples in R, and so far, any questions? How to generate 1,000 Bootstrap data sets. So basically join balls with replacement. So, and then the next step is just to put those in the results of the number of balls as the indices to generate the new data. So that's exactly the idea, but we can generate 1,000 data sets. So now let's just consider to have a look. So how can we use these 1,000 Bootstrap data sets to accomplish something similar in simulation? So one natural question here is that, because if you still remember, we can use the 1,000 simulation to approximate distribution of beta 1 hat, and also we can approximate standard deviation of beta 1 hat, right? So that's the advantage of one simulation. So similarly, can we use this similar idea, but use 1,000 Bootstrap data sets instead of the simulation data sets to approximate the sampling distribution or to approximate the standard deviation of beta 1 hat? And the answer is yes. So these are the Bootstrap data sets. So based on each data set, we can fit Poisson log linear regression model and obtain the maximum likelihood estimation. So that means for the first data set, we can obtain our first maximum likelihood estimation of beta 0 and beta 1. So here, in order to keep consistent, so we also use star notation and parenthesis notation to help us understand that it's actually from the Bootstrap data set number 1. And the last one here is from the Bootstrap data set of number R. R equals to 1,000. So we will have 1,000 different values of maximum likelihood estimation. So something similar, right? So the only difference here is we use 1,000 Bootstrap data sets. We do not use the simulation data sets. So how can we realize that? So if you look at the code, the R code here, they are exactly the same compared to the simulation part. The only difference here is that we use Bootstrap data set. So this is the only difference. So this is the only difference. We just put our Bootstrap data sets here in, if you still remember the simulation R codes, and then we can obtain 1,000 different estimations of beta 0 and beta 1 by using the Bootstrap data sets. And if you still remember simulation, we can use the 1,000 different MLEs to approximate the sampling distribution of beta 1. So here, similarly, we can also use this 1,000 MLEs from Bootstrap data sets. So those are from Bootstrap data sets. And we can use these values to approximate the sampling distribution. So that means if we try to draw the histogram of this beta 1 star, so this hat beta 1 star saves the values of these different beta 1 hat. So basically we just save the coefficients here in this beta 0 star and beta 1 star vector. So if we just draw a histogram of this beta 1 star, we can use this histogram to approximate the sampling distribution. So if we know the distribution, we basically know everything, if you still remember. If we know the distribution, we can compute the standard deviation. So the standard deviation of this beta 1 hat can also be approximated by using these 1,000 values of beta 1 hat based on bootstrap. So if you see the star, so basically that means bootstrap. So this standard deviation of hat beta 1 star here can be an approximate of the standard deviation of beta 1 hat. And you can find that this value, this standard deviation here, or you can consider it as the standard deviation of the 1,000 MLEs. So this standard deviation is from the bootstrap sample. But if we compare this to the standard deviation, so this is from the simulation. So for simulation, we actually need to know true values of beta 0 and beta 1. And we can obtain this approximate of the standard deviation. So it's also an approximate of But in order to get this approximation, we need to know the true values of beta 0 and beta 1. But to obtain this standard deviation based on bootstrap, we do not need to know beta 0 and beta 1. So what we need to do here is we only need one data set and 1,000 we only need one data set and drawing balls with replacement. So that's the difference. But by comparing these two, we can actually find that the standard deviation here, by using the 1,000 repeat bootstrap, so by using our drawing balls with replacement idea, we can actually approximate the standard deviation of beta 1 hat very, I think, very accurately, even if we actually have no idea about beta 0 and beta 1. So it's actually the case for real data. So that means for real data, we can also approximate the standard deviation of beta 1 hat by using this bootstrap idea. So in this case, we call this the standard deviation by using the 1,000 bootstrap maximum likelihood estimation values. And we can call this the bootstrap standard error of beta 1 hat. And we can use the notation, the standard error B, so basically means bootstrap standard error. So that means by using this bootstrap method, we can give a good estimate of the standard deviation of beta 1 hat. And also note that we do not have very large sample. We only have a small sample. So that means this method can work for the small sample problem to approximate the standard error. And let's just compare the bootstrap standard error and also the approximate standard error, if you still remember. So this comparison is both under the situation of James. So that means we only have one data set in real application. So if we only have one data set, so basically that's what we face in the real application. So we can actually use the summary output to obtain the approximate standard error, if you still remember. And we have never talked about this formula, how to obtain this formula, because it's complicated. But R can actually provide these results, these values of this approximate standard error. And what I can tell you here is that this approximate standard error is a very good estimate of the standard deviation when the sample size M is very large. But in this case, because we do not have a very large sample, so in this case, in our output, this approximate standard error cannot be used. So if in the final exam, you find a small sample case, and also I provide the summary output from R, and you can see the approximate standard error in the R output. So in this case, you should have this conclusion that because we have a small sample, so usually if the sample size is larger than 30 or 50, so usually we consider it as the large sample size. But if the sample size here equals to 10, basically it's small. So in this case, we can never use the R output standard error because it's no longer accurate. So the approximate standard error here is obtained based on M is very large. But the bootstrap standard error, so that means what we have done here in the whole procedure to obtain this, so this is the bootstrap standard error, can still be used under the small sample case. And also you can show that, or you can use Professor Peter Hall's book to have a read, and you can obtain this conclusion. When the sample size M is large, the bootstrap standard error can also be used. So in this case, we summarize the use of these two standard errors in this table, I think mostly for generalized linear model. So that means even if in this example we only show the Poisson log linear regression model, but actually the use of the bootstrap standard error is not limited to Poisson model. So basically it can be used for all the models, all the generalized linear models. So the conclusion is here. So if we have the same we have the sample size, small sample size, so that means small m. So in this case, we should consider to use the bootstrap standard error. But if we have the large sample size, we can both use the approximate standard error from our output, or we can perform this drawing balls with replacement idea to obtain bootstrap standard error. So we can use both. And in conclusion, so why we need to introduce bootstrap? So because when we consider to use the bootstrap, we can realize the benefits from simulation, that we can actually estimate the sampling distribution of parameter estimation, and also we can estimate the standard deviation of the estimation. And the estimating result here is the bootstrap standard error. And usually the standard error can be used to help us to measure the accuracy of some estimation, which is really important in our inference problem. And also, by using the bootstrap idea, we do not need to use any formulas. And if you remember, this approximate standard error is actually from some formula, but we have never mentioned about it because it's complicated. But if you can understand the idea of bootstrap, you never need a formula to compute the standard error. So what you need to do here is just to use the drawing balls with replacement idea to generate 1,000 bootstrap data sets. And also here, the sample size M can be large or small, it doesn't matter. So you can, basically, when M equals to 10 or M equals to 30, you can both use you can use the Bootstrap standard error for both situations. And I think the only disadvantage here is to generate 1,000 data set, because you need to generate 1,000 data sets. So in that case, that will be computationally intensive. So that means it takes time to obtain the Bootstrap standard error. But with the development of the technology, I do not think it's a problem. At least I do not think it's a problem in this course. So that's, I think, basically the first part of today's lecture, to use the Bootstrap idea to compute the Bootstrap standard error in order to estimate the standard deviation of some estimation. So any questions for this Bootstrap standard error, the first part of Bootstrap? So by using one sentence to conclude this part, so basically what we have done here is just to replace the simulation data sets with the Bootstrap data sets, and then use the exact same idea to obtain the approximate of the standard deviation. Okay, let's just take 10 minutes break, and then we are going to talk Bootstrap confidence interval. Okay, let's start the second part of today's lecture. And in conclusion, so basically today we talk about the idea of Bootstrap, but if you can understand simulation, you will find that the only difference between Bootstrap and simulation is that for Bootstrap, we generate the data by using drawing balls with replacement idea. But for simulation, we generate the data by using model assumptions and also the true value of parameters. So this is the only difference. And any questions for Bootstrap idea? But I think another very important difference between Bootstrap and simulation here is that Bootstrap is actually proposed to deal with the real data problem. So that means in our real life, we usually have one data set in this case. So Bootstrap idea is proposed to help us to deal with the real data problem, to obtain the standard error of the estimation based on one data set of real data set. And also we can use the Bootstrap idea to obtain the Bootstrap confidence interval. So in order to obtain the confidence interval, firstly, let's just firstly talk about some review of confidence intervals. So if you still remember, in the generalized linear model, we used to talk about this practical sampling distribution. So that is the estimation minus the true value of beta j divided by the approximate standard error is approximately standard normal distribution. But we only have this approximation when m is large, when the sample size is large. And if we have this approximation, we can obtain the 1 minus alpha confidence interval, which is beta j hat minus plus the quantile. So here, z alpha divided by 2 is a 1 minus alpha divided by 2 quantile of the standard normal distribution times the approximate standard error. If you still remember this approximate standard error and also this practical sampling distribution, they can only be used only when m is large. So a natural question here is that if m is small, how can we obtain the confidence interval? If you still remember, in Bootstrap, we mentioned that when m is small, we can actually use the Bootstrap standard error. So in this case, when m is small, we can also use the Bootstrap idea to obtain Bootstrap confidence interval. So the name here is called Efron's percentile Bootstrap confidence interval. So I will explain why it's called percentile Bootstrap interval, a Bootstrap confidence interval. And Efron is another statistician who has a huge contribution in Bootstrap. So I think in the reference we have mentioned about Efron. So Efron is a statistician in Stanford. And I think he is the first person to propose this idea of Bootstrap in statistics. And Peter's work, Professor Peter Hall's work, is basically to confirm that this method, this brilliant idea, actually works from the theoretical point of view. So Efron firstly proposed this percentile Bootstrap confidence interval. So let's look at how can we obtain this kind of confidence interval by using the Bootstrap idea. So firstly, if you still remember, we can use the 1,000 different values of the maximum likelihood estimation based on the Bootstrap data sets. Here we have star. Star just means it's obtained by using the Bootstrap data set. And we have these 1,000 values, and in that case, we can use these 1,000 values to estimate the sampling distribution of beta 1 hat. So what we can do here is just to use this histogram to approximate the sampling distribution. And if we have the distribution, so basically we have everything. So in the earlier case, for the bootstrap standard error, we use these 1,000 values to obtain the standard deviation. Now let's just look at how about we use this 1,000 different values of the maximum likelihood estimation to obtain the quantiles, or in other words, percentiles. So we have these 1,000 values of maximum likelihood estimation, and which are saved in this vector head beta 1 star. So that means head beta 1 star, if you still remember the bootstrap procedure, this vector consists of 1,000 different values of beta 1 estimation based on bootstrap data set. So by using this quantile function, we can actually obtain the 97.5% percentile of this head beta 1 star. So this is the 97.5 percentile of head beta 1 star. So here we set alpha equals to 0.05, and 1 minus alpha divided by 2 equals to 97.5%. And similarly, we can also obtain the 2.5% percentile of the vector head beta 1 star. So that means we can actually obtain these two quantiles. Two quantiles or two percentiles based on the 1,000 different values of beta 1 head by using the bootstrap data sets. And then if we just put these two percentiles together, so we put these two percentiles together, and then we call this the interval between these two percentiles as the percentile bootstrap confidence interval. So this is exactly the percentile bootstrap confidence interval for beta 1 with this confidence 1 minus alpha equal to 95%. So basically you can see the relationship here is 97.5% minus 2.5% equals to 95%, right? So straightforwardly, by using this bootstrap estimation of beta 1 head, we can obtain this percentile bootstrap confidence interval. Because we use percentile, so we call it percentile bootstrap confidence interval. That's straightforward, right? So we only use the two percentiles of this bootstrap estimation of beta 1. And also, because if you still remember, we consider the Poisson log linear model. So the model is log mu equals to beta 0 plus beta 1 x 1 or x. So we are also interested in the confidence interval for this exponential of beta 1, which is the multiplicative factor, if you still remember, in the interpretation of this Poisson log linear regression modeling. So if we are interested in it, so in how to obtain the bootstrap confidence interval for this exponential of beta 1, that is also not hard. So what we need to do here is just to exponential the interval here, exponential of the interval of beta 1 directly, and then we can obtain the bootstrap confidence interval for exponential of beta 1. So if you still remember, this method is consistent with the method, I think, in the inference topic, if you still remember, for generalized linear model. So if we want to obtain the confidence interval for exponential of beta 1, we just exponential the original confidence interval directly. So that means here, this 2.1 here equals to the exponential of 0.7433, and this equals to exponential of 2.0305. So those two values are from the previous percentile bootstrap confidence interval. So that's the bootstrap confidence interval. Any questions? Just obtain the percentiles or quantiles directly. Okay, let's look at another example. So in that case, I think you can understand it more clearly. So in this example, we are interested in obtaining the confidence interval for mean of response. So if you still remember, we actually obtained the confidence interval for mean of response, but only for multiple linear regression model, right? But we never talk about how to obtain the confidence interval for mean of response for generalized linear model. I think the reason is obvious because the formula is too complicated and I cannot give it to you. But after we know Bootstrap, I think it's no longer difficult because the benefit for the Bootstrap here is that we do not need to know the formula. So what we need to do here is just to generate 1,000 Bootstrap data sets. So recall that here we are interested in mean of response. Recall that for Poisson log linear regression model, so the model can, I think the linearity assumption can be written in this way. And in this case we can obtain the mean. So this is actually the mean of response. So this is the mean of response given values of x1 to xk. So this is the mean of response for the Poisson log linear regression model case. So it's different from the case in the multiple linear regression model. And by using the maximum likelihood estimation and also by using the plug-in idea in statistics, we can obtain this plug-in estimation for the mean of response. So this is exactly the estimation. And the question here is that can we use, so we never mention about the sampling distribution of this. We only talk about the sampling distribution of beta 0 hat, beta 1 hat, and so on and so forth. And also we do not give the formulas for this sampling distribution. So obviously we cannot give the formula here in this course because it's a little bit complicated. Because we have no idea about the sampling distribution of this estimated mean of response, so we cannot obtain the inference of the mean of response correspondingly. So a natural question here is that can we use the Bootstrap idea to obtain the confidence interval of this mean of response mu? So we want to obtain the mean of response, which is the mu, the confidence interval of mu z given x, based on this 1,000 Bootstrap data sets? And the answer is yes, and you will find that it's actually not that hard to obtain it. So how to do that? Firstly, we have 1,000 Bootstrap data sets, and secondly, we can fit a Poisson log linear regression model. And after we obtain the fitting, we should have the 1,000 different values of parameter estimation, maximum likelihood estimation. So we should have beta 0, star 1, beta 0, beta 1, star 1. So that's the maximum likelihood estimation for the first data set. And also we have beta 0, star 1,000, and also beta 1, star 1,000 for the 1,000th Bootstrap data set. So for each data set, we have estimation. And also we have hat because it's estimation. And by using the estimation, if you still remember, if we plug in the estimation and also those given values of x1 to xk, we can obtain the estimated mean of response. So that means here, by using this given value x equals to 0.25, and also the value of the estimation, we can actually obtain the estimated mean of response for each Bootstrap data set. So that means we will have 1,000 different values of the mean of response, estimated mean of response. So in order to realize that in R is also not hard. So what we need to do here is just to use this. Firstly, we need to keep some space to save this 1,000 values of mu hat. And then in the loop, we just use the GLM to obtain the fitting result. So this is the fitting result. And then we just put the fitting result here. So this is the GLM fitting result, as well as the value here, the value 0.25. So which is the value we give to obtain the mean of response. But remember that when you use this predict function, you need to be very careful because you need to keep the same with the, I think, with the variable names. But here, I have already solved this problem for you. So just understand it, I think it's enough. And in this case, you can use this predict variable to obtain the estimated mean of response. So here, you actually obtain mu hat star lowercase r, because it's inside the loop. But the lowercase r here is from 1 to capital R. So in that case, you obtain 1,000 different values, and you save those 1,000 different values in this hat mu star vector. And in this case, you have 1,000 values of mu hat star. And no matter the sample size m is small or large, we can use this histogram to approximate the sampling distribution of mu hat. So mu hat here equals to exponential of beta 0 hat plus beta 1 hat plus times x, and x here equals to 0.25 or 0.25, I think. And this is the sampling distribution. So you can see it's a skewed distribution, it's not normal. But it doesn't matter, we do not need to know the exact distribution. So what we need to do here is just to use these 1,000 values to obtain the percentiles. Firstly, we obtain 97.5 percentile of these 1,000 values. And secondly, we obtain 2.5 percentile of these 1,000 values. And then we just put this together. And in this case, we obtain this percentile bootstrap confidence interval with the confidence 95%. Just obtain the percentiles of these 1,000 values of mu. So that means even if we have no idea about the sampling distribution of the estimated of mean of response, for the Poisson log linear regression model, we can still obtain the the confidence interval for mean of response. So that's the advantage, basically, for the bootstrap confidence interval. So no need for formula, and this can be used no matter the sample size is large or small. So what we need to do here is just to generate 1,000 bootstrap data sets, compute 1,000 different values, and then obtain the percentiles and use those percentiles as the confidence interval. Any questions for, okay. So prediction interval. Okay, the student asked a very good question. So can we use this to obtain the prediction interval? Can we use the bootstrap idea to obtain the prediction interval for the mean for the Poisson log linear regression model? I think that's a quite good question. So what I can tell you here is that I think in order to obtain the confidence interval, I think it's straightforward. So that means we need to get the 1,000 we need to get 1,000 different values of mu hat, right? So similarly, if you really want to get 1,000, you need to get the prediction interval, but not confidence interval. So firstly, you need to review a little bit here is that this is the mean, this is the estimated mean of response, right? And also we can use this to as the rough prediction, but it's only rough prediction because the Poisson log linear regression model for that can only take values of integer, right? So that means we can use this estimated mean of response to predict that. We can do that, but it's only a very rough prediction. So if we can, we really need to obtain this kind of, if you want to use the bootstrap idea to obtain the prediction interval. So what you need to do here is that firstly obtain this 1,000 different values of mu hat. And secondly, you need to consider to use some kind of combine the bootstrap idea and also the simulation idea. And it's actually called parametric bootstrap. I think it's a little bit beyond the scope of this course. So what you can do here is just to use this mu hat star 1 and generate y, for instance, y, maybe z is, but I'm not sure about, I think y is more appropriate. Generate y1 star from the Poisson distribution of this mu hat star 1. Maybe let's use y star 1. And also you can do that to generate y star 2 and onto y star 1,000. So the reason here why we can call it parametric bootstrap here is that we actually use some model information. It's a little bit different from the, I think, the classical here. So basically what we have talked about in this course, in these lectures, we focus on the non-parametric bootstrap, but I think it's totally beyond the scope of this course. So what I want to say here is that you can use those mu's to generate y by using the Poisson distribution. And the next step is just to obtain the percentiles of these y's. And in that case, you will obtain the percentile prediction interval in this case. But I think basically it's beyond the scope of this course. So you can do that, but you need more steps. You need to use those mu's to generate y. Those are integers. By using our model assumptions to obtain the prediction interval. So I think it's beyond the scope of this course, so obviously it's not required. It's not required in your final exam. So what is required in your final exam just to understand how to compute the confidence interval by using the bootstrap idea for the mean of response. Any questions? So let's just try to conclude. So basically, the benefits here, I think, are almost the same as the bootstrap standard error. So basically, we do not need to use the formula. And what we need to do here is just to generate 1,000 bootstrap data sets and obtain 1,000 different values of estimation, and then just to use the percentiles of the estimation, the 1,000 different values of estimation to be the confidence interval of the corresponding parameter. So that's the exact idea. And similarly, we have a table to help us, to guide us to use whether or not we use bootstrap confidence interval or we use the classical confidence interval by using the standard error. So when m is small, when the sample size is small, so obviously we should use bootstrap confidence interval. But when m is really large, we can use both. We can use either of bootstrap's confidence interval or the classical confidence interval based on the standard error. So I think that's basically the last part of bootstrap. And what I need to give you the final note here is that this method is not limited to small or large sample. So basically, it can work for small or large. It doesn't matter. And also, it's robust to normal or non-normal. So that means if we do not have the normal assumption, we can actually use the bootstrap to obtain the standard error and also confidence interval. Especially, I think, if you still remember in multiple linear regression model, we mentioned that all the inferential tools, including hypothesis testing and also confidence intervals, are based on the normal assumption. But if we do not have the normal assumption, we can still use the bootstrap idea to obtain the confidence interval. Also for multiple linear regression model. And also basically for all the generalized linear regression model, we can implement this idea to obtain the standard error and also the confidence intervals. And we actually have more to talk about bootstrap. So for instance, what I have mentioned earlier, so what is the difference between the non-parametric bootstrap and parametric bootstrap? Something like that, but it's beyond the scope of this course. So what you need to know here is just to know to use bootstrap to compute the standard error and the confidence interval, especially when the sample size m is small. So that is the requirement in this topic. So basically, if you can understand the lecture notes, if you can understand what I am doing by using those R codes, I do not think there is a problem. Any questions for bootstrap? Okay, I think it's basically the end of bootstrap, so let's just take very brief 1-minute break, and then we are going to talk about our last topic, principal component analysis. Okay, let's start our last topic of this course, which is principal component analysis. I think for some, especially for the statistical major students, I think they may have learned it in some other courses, for instance, statistical learning or the other courses. But I think for most of the students, especially for the non-statistical major students, I think I still need to mention it a little bit about some basic analysis, I think, in multivariate data, so which is called principal components analysis. And firstly, we are going to use some motivating example, and then we are going to talk about what's the meaning for PCA and what can we use for PCA. And so firstly, let's just look at this test score data, which is really close to our real life. So the data set is in this text txt file. So for txt file, I think maybe it's the first time in this course we use this txt file, but I think you will find that the using of this txt file is, I think, basically similar to the using of CSV file. And for this data set, we actually have the examinations of 25 graduate students in a US university. And we have, in this data set, we have 5 subjects. We have the differential geometry, complex analysis, algebra, real analysis, and statistics. So basically, all math courses. So you can think that those students are obviously from the School of Mathematics. And in order to read this txt data, we use this read.table function. So we just put the .txt data in, and also we need to specify head equals to t. So that means the first row consists of column name. So that means the first row here is the name of different subjects: the differential geometry, complex analysis, algebra, real analysis, and statistics. And we have 25 students, so that means we have 25 observations. And also we have the grade for each student. So basically the data consists of the grades of different students. And also, I think in this data set, we give some extra information. The first two, the differential geometry and also the complex analysis, these two are our closed book exam. So these two are closed book exam. And these 3 are open book exam. And also in this course, you can actually take 2 pages of A4 notes with notes on both sides. I think you should note that, I think, from your email. So that means this, for our course, applied statistics, it's half open book exam. So different from this 5 subjects. So here we have these grades of different students of different subjects. So now let's just talk about so what kind of data it is. So here, if we consider this tuple, we consider the differential geometry, complex analysis, algebra, real analysis, and also statistics in a tuple. So in this case, we can call it multivariate data because we have different variables. So for this kind of multivariate data, we actually have a lot of tools to help us to analyze it. We have PCA, we have factor model, we have cluster analysis. So actually, we used to have a course which is called multivariate analysis in our school, but because no students wanted to enroll in that course, so that course was canceled. I think the reason why we do not have that course here is there are 2 reasons. The first reason here is that in order to understand the multivariate analysis in statistics, I think the algebra is required, the linear algebra is required. So you will find that, I think, even though I try so hard in this topic to keep away from linear algebra, but we still need a little bit to help us. And the second reason is that I think for multivariate analysis, we have a new popular name, which is called unsupervised learning. So you will find, I think, maybe in later, I think we talk more about learning instead of the classical statistical terminologies. For instance, we have supervised learning to replace regression, and also we have unsupervised learning to replace multivariate analysis. So we still have multivariate analysis if you enroll in statistical learning. But I do not think a lot of students will enroll in statistical learning, I think, next semester. So we still talk a little bit about PCA, I think, in this course. So the idea for PCA here is basically from dimension deduction. I think because this case, you can consider this example is a toy example. So you may not find the need to reduce these five variables into maybe one or two variables. You may not have a lot of incentive to do that. But if you know that we actually have a school here which is really strong in ANU, which is the Medical School of Research. So if you consider some biology analysis, for instance, the gene analysis, you will find the need to reduce, for instance, I think for genes, we need to reduce maybe millions of genes into one or two important variables. So I think the idea for the PCA here is actually to reduce the dimension, which is called dimension deduction, or in this case, we want to use one or two variables to summarize these five variables. So that's the idea. And I think this idea, it can be implemented very easily. So that is what you have done I think, in your GPA. So basically use some mean test score, in this case, which is the linear combination of the original 5 scores with equal weights. And then we use this one score to represent the information of these 5 scores. So that's the idea. We want to reduce the number of the variables for this multivariate data. But instead of this mean score, so I think it's straightforward and everyone can understand it. So can we use other kind of linear combinations to generate another kind of overall score? But we need to consider some standard from statistics. So we consider to find some linear combinations which contains the most of the variation information of the data. So that means we want to find one or two variables to contain most variation of the original data set. So that's our purpose. So how to do that? We need to consider this principal component analysis. So basically, what's the PCA? PCA just use some methods to find some linear combinations of the original data set to capture most variation information of the data. And this is very useful if we consider, for instance, to reduce maybe millions of genes information into one or two variables. So that's basically something we need in our big data era. So we have millions of variables, but we only need one or two because people can only understand very less information from the data. So in order to accomplish this, we need to talk about what is the linear combination. So linear combination, I think straightforwardly, we just consider a linear function of the original variables. And for instance, originally we have 5 variables in our case. So we denote it by using x1 to xk. Then in this case, we can just write z as a linear combination, which is the linear function of x1 to xk by considering the coefficients c0, c1 to ck. Or we can call those weights. So if you consider your average score, the mean score, so basically we consider the equal weight. So we can consider z equals to 1 divided by 5, x1 plus 1 divided by 5, x2 plus so on and so forth until 1 divided by 5, x5. So what we need to do here is just to consider different weights. So for PCA, we actually need to consider k different linear combinations. So the reason why we need to consider k different linear combinations is that we originally have k variables. So let's firstly consider this symmetric case. So that means we try to transform our originally k variables x1 to xk to this z1 to zk. So that's the first step. So how to do that? So that means we need to consider a lot of coefficients. So we can consider the first group of coefficients to obtain the linear combination Z1, and also we can consider those coefficients to obtain our the second group of the coefficients to obtain our second linear combination Z2, and so on and so forth until we get the last Zk. So after that, after we define the linear combination very clearly, so let's just look at how to achieve our goal. So if you still remember, we want to use the linear combination to capture most of the variation of the data. So that's our purpose. But in order to easily discuss it, firstly, we have our requirement 1. So this requirement 1 means that we need to find those coefficients Z10 to Zkk. We have a lot of coefficients such that these linear combinations Z1 to Zk are not correlated. So that's the first requirement. So that means, firstly, we need to select the weights such that this Z1 to Zk are not correlated. So the reason why we need to do that here is actually to help us to understand something. Because if Z1, for instance, if Z1 and Z2 are not correlated, so that means from the linear understanding of the variables, so that basically means Z1 and Z2, the correlation of Z1 and Z2 equals to 0. So basically, you can consider that for instance, the increase of Z2 will not affect the value of Z1. So that means Z1 and Z2 are totally separated, you can consider in this case. But for our original data, x1 and x2, we do not necessarily have this kind of property. So that means x1 and x2 can be correlated. The correlation of these two can be not equal to 0. But after we consider the transformation, we should consider these two principal components are not correlated, which is easier for us to interpret the data, to separate these two variables. So this is the first requirement. And then, based on the first requirement, we try to accomplish the maximum variance information idea. So the second requirement here is that we actually need to select the values of those weights 0 to C1k. So those are weights of Z1 such that we maximize the variance of Z1. So that is the meaning here. We want to get Z1 such that we capture the most of the information, most of the variance information to maximize the variance. So basically, by doing that, by selecting those C1, those weights, we can obtain Z1 has the most of the information. And then we need our requirement 3 actually to determine Z2. So how can we do that? So basically, we select the values of C20 until C2k. Those are weights of Z2 such that we also maximize variance of Z2, but we consider constraint. So the constraint is actually in the beginning. So subject to just means constraint. The constraint here is that the Z2 and Z1 should not be correlated. So we still maximize the variance, but we need to consider some constraint. So that means instead of Z1, you can consider that instead of Z1, we need another variable Z2, which is not correlated with Z1. So basically, Z1 and Z2 do not have any relationship. But we still need to maximize the variance of Z2. But how to accomplish this task? So how to select those C? So that's basically the problem to solve in the PCA. And similarly, we can consider requirement 4, so that's for Z3. So what we need to do here is just to select C30 to C3K such that the variance is also maximized, but we need to consider more constraints. So that is Z3 and Z1 are not correlated, Z3 and Z2 are not correlated. So we need to keep on doing that until the last principal component, Zk. So basically, those are requirements to determine those weights. So based on those requirements, we can keep on working on those requirements. So we can obtain the weights of Z1, which is C10 until C1K, and also we can obtain the weights of Zk, which is also from K0 to CKK. And we have a lot of weights, and we can denote those weights in a matrix, and we can call this matrix loading matrix. And those weights are called loadings of principal components. And also, what's the principal components? So the principal components is our Z1, which is equal to C0 plus C11 x1 plus so on and so forth until C1k xk until Zk. So K principal components. So principal components just means those Z value. Ck0 plus Ck1 x1 plus so on and so forth, Ckk xk. So after those weights are computed based on all the requirements, so we can obtain the principal components, we can obtain K principal components Z1 to Zk, and also we can obtain the loading matrix. So how to compute those? So the problem becomes how to compute those weights based on those requirements. So what I can tell you here is that I will not talk about the linear algebra behind it, but what we can do is just to use R to compute those weights. So how can we do that? We just use this principal component function directly, and then we can obtain those weights. And I think in my next lecture, I will talk about how to obtain those weights. So basically, if you use this function appropriately, you will obtain the weights. So these are the weights. And I think I will talk more details next week about how to use R. But by using one sentence to conclude what are the principal components. So the principal components are basically linear combinations. So firstly, it's basically the first sentence. They are linear combinations of the original variables. And secondly, in order to we have some requirements for those